We're talking about logarithms today. Last week we worked on some problems that looked like this, where we had a variable in an exponent and we had to solve to figure out what the variable would be. And we can do that using some pretty basic math if we can create an equation where we have like bases on both sides, okay? Or if we have things that work to good exponents. But sometimes we have to solve for a variable in an exponent in a really ridiculous number, like this. 5 to something equals 34. And I know it can't be 2 because 5 squared is 25. And it's not 3 because 5 cubed is 125. So it's somewhere in between 2 and 3, and it's closer to 2. There's no way to know what it could possibly be. And it's actually a super irrational number. It's like 2.19116432, and the number goes on forever, okay? But we need a way to solve this because there are things in the world that grow exponentially, and we might need to know what the exponent was that got us to that number. So we have something called logarithms that come into play when we need to do this. A logarithm is an inverse of an exponent. Okay, so it's kind of like when we're solving equations, if we have addition, we can use subtraction. If we have multiplication, we can use division. If we have exponents, we can use logarithms. And if we have logarithms, we can use exponents. So the first thing we're going to learn is how to take something written as a log and rewrite it as an exponent, and then we're going to go back and forth. Because if we have it in log form and we can't solve it, we can switch it to exponential form to solve. If we have it in exponential form and we can't solve it, we can switch it to log form and solve. We can go back and forth between the two. One of them will be solvable. One of them will seem very confusing. Okay, so to go back and forth between a logarithm and an exponent, we do what's called a log roll. I have a statement here written in logarithmic form. Normally, b would be a number, a would be a number, x could be a number, or it could be my variable, my missing number. But when I read this, I say log base b of a equals x. To change it to exponential form, so I'm going to create an equivalent equation that's written as an exponent with no log. The thing that I remember is I start at my base and I roll around like so. Okay? So I start at my base, and that becomes the base in my exponential equation. And then the other thing I remember is that a log solves for an exponent. So this guy at the end is my exponent. And this value is what the exponent would equal. So equals a. Okay, so two ways to write the same thing. And then depending on where my variable is, I choose one form or the other so that I can calculate it, so that I can solve it. Okay, so we're gonna practice rolling into an exponent. Then we're gonna practice rolling back to a log so we can move back and forth between the two. I'm looking at number 1. It says log base 3 of 9 equals 2. If I look at my roll, I start with my base, log base 3. 3 is the base of my exponential equation. A log equals an exponent, so my exponent is 2. And my value right here becomes my ending. And we can go back and forth between the two. Now, I don't have any variables right now, so it's kind of just like, well, yeah, 3 squared is 9. Yep, and log base 3 of 9 equals 2. So depending on which value I was missing, I would determine which version I should use to solve. So let's do another one. Number 2 says log base 6 of 216 equals 3. We're going to start at our base, which is 6. Roll to our exponent, which is 3. 6 cubed is this value right here, 216. Go ahead and try the next two if you would, please. And check your work, see how you did. Now, fun fact, log base anything of 1 always equals 0. So when we get into the solving of logs, if you can somehow create a log of 1, it eliminates your term. It always equals 0. 2 to the 4 equals 16. And these last two, when we roll this, log base 4, 4 to the negative 2. Remember that negative exponent creates a fraction, and it would be 4 squared at the bottom of my fraction. And it does, in fact, equal 1/16. We're going to be filling in some numbers here pretty soon. So pay attention to where how our negatives behave, and then also how our fractions behave. So here I have 9 to the 3/2 equals 27. And just to remind us, if we have a fraction up here, it's exponent over index. So this would be like taking the square root of 9 cubed. That's how it equaled 27. Okay, now we're going to go the other way. We're going to have exponential equations. We're going to turn them into logarithmic equations. The base of our exponent is the base of our log. So if my base here is 14, I'm going to have log base 14. And the log statement equals the exponent. Okay, that exponent's going to go last. And it really does a roll again. So log base 14 of 196 equals 2. Number 8, I have 3 to the power of 4 equals 81. 3 is my base, so I'm going to write log base 3 of 81. That's the answer to my exponent. And it equals the exponent. Log base 3 of 81 is 4. Try the next two, please. Check your work, see how you did. Another good one here, when you have a base and a value that are the same, regardless any base, any value, if these match, it always equals 1. So when we get to where we're condensing and expanding and doing all these solving with log statements, if we can create something where the base and the value are the same, it turns into 1. Like it's a really easy solve. Okay, last two, log base 2 of 1/8 is negative 3. And log base 8 of 16 is 4/3. Turn the page when you're ready. Alright, now you have a log button in your calculator, but it's kind of limited on what it can calculate. If you look on your calculator to the left of the number 7, you'll see a button that says log. Okay, this is a common log. It doesn't do log base 3, it doesn't do log base 5, it does common log, and a common log is log base 10. When we have something as log base 10, we're in a base 10 number system, okay? Everything that we count up to 10, and then we carry, and then we count up to 100, and we carry. We're in a base 10 number system. So we work in log base 10. We just call it log of x. And so the log button in your calculator does log base 10. It doesn't do all the other logs, but I'll show you in a little while how to work around that so you can use your calculator for this, okay? But it's called a common log. We write it without that little 10. Anytime you see log without that little 10, it's log base 10. All right. So now we're going to evaluate some. And the first set that we're going to evaluate, we're going to be able to mental math. And then we're going to get to some that have really strange, wacky numbers that we can't mental math. We have to do a little more with. So looking at number 13, it says log base 7 of 49. And I just need to know what the answer is. How much is this worth? So what I'm going to do is I'm going to say, well, if this equals x, I want to solve for x. And I'm going to turn it into an exponential equation. So I'm going to take my base of 7 to the power of x equals 49. And that looks like something I can solve. What does x have to be? 2. So the value of log base 7 of 49 is equal to 2. Okay, trying number 14. 3 to the power of something equals 27. What does it have to be? 3 squared would be 9. 3 cubed would be 27. So the value of log base 3 of 27 is 3. This one we can mental math or we can put in our calculator because we have a log button. But log base 10 says 10 to some exponent equals 100. What does my exponent have to be? 2. Number 16, log base 12 of 1. This is another one that we're going to get to the point where we can automatically know the answer. It is 0. Anything, log base anything of 1 is 0 because my exponent has to be 0 for my value to equal 1. Try those next 4 if you would, please. And if we know it's going to be a good number and we're just like not quite sure, like 3 to the something, I'm like, is it 3 cubed, 3 to the 4th, 3 to the 5th? Just start typing them in your calculator. Calculate some exponents, see what gets you there. Now these last two, if you got them, fantastic. 9 to some exponent equals 1 over 81. Because it results in a fraction, my exponent has to be what kind of number?
Negative.
A negative number. And to make 9 be 81, it would have to be a negative 2. And last one, 64 to the power of something equals 4. Right here, my number got smaller. It didn't turn into a fraction, so it's not a negative exponent. What I did is I took a root. So I have a fraction exponent. So it's going to be 1 over something. Which root of 64 is 4? Does anybody know?
8. 3.
64 to the 1/8.
3.
64 to the 1/16.
45. Yeah, it's 3. It's 45.
64 to the 1/3. The cube root of 64 is 4. 1/3. That one is a harder one to find, I know. But use this strategy where you put some numbers in. And if your answer's way off, choose a different number. Okay.
Wait, so what does x equal on that one?
1/3. Sorry, I just wrote it really weird for some reason. There we go. All right. So now sometimes we're going to have some that our regular math just we can't mental math it. It's not a good number. Maybe it's an irrational number. Maybe it's a fraction, but it's an improper fraction and we can't quite find what it is. We know that we have this log button in our calculator, but it only does the common log. It only does log base 10. I need log base 16, and I need log base 8. So we have a change of base formula that will turn log base anything into log base 10 so that we can calculate it on our calculator. So if we have log base b of a, b and a would be numbers, I can divide log of a divided by log of b. I can use that base 10 button in my calculator, and it will solve for that exponent every time. So looking at 21, it says log base 16 of 64. What the question is 16 to some exponent equals 64. I don't know. It's not 16 squared. It's not 16 cubed. It's actually the square root of 16 cubed, but I can't just come up with that in my mind. So I use the change of base formula here, log of 64 divided by log of 16. I use the log button in my calculator, log 64, and make sure you close your parenthesis right here, and then we do the division button, and then log 16. It will give you the wrong answer if you forget to close that parenthesis, and I hit enter. The square root of 16 cubed. You can give me the decimal here, 1.5. You can check your answer by going back to your exponential equation. 16 to the 1.5 is 64. But that change of base formula will work every time when you have one term and it's not a base 10. So let's try number 2. Log of 32 divided by log of 8. Now, don't divide your 32 and your 8, okay? Make sure you're putting the whole bit into your calculator. Log of 32 divided by log of 8. I get 1 2/3, 1.6 repeating. And I could check this one. If I did x to the answer, it would take me back to that 32.
Could you just put it in improper fraction?
Yeah, you definitely could. There we go. 5/3. Yep, definitely. Sometimes you're going to get a really ugly irrational number. A lot of these will be irrational. Looking at 23 log of 54 divided by log of 2. When I put that one in my calculator, I get it. So irrational means this decimal goes on forever. It can't be written as a fraction. That's okay. I'm going to do these ones to 4 decimal places so that we can get as close to accurate as we can. When we get to graphing them, 5.8 is good enough. But when we're evaluating let's do 4 decimal places so we have an accurate value. So this is going to be 5.7549. Okay, looking at 24, this is log base 10. So we could definitely do log of 294 divided by log base 10 of 10, or log of 10, but we're dividing by 1. We can also, if it's log base 10, that's exactly what your calculator calculates. You'll get the same answer either way. So I'm going to round that to 2.4683. Try the last two, please. And that bottom one, number 26, that's one that you could mental math. 6 to the what is 1 over 36. Both things are going to get you the same answer. So you can really choose if it's an easy one and you want to just solve it in your head, have at it. Turn the page when you're ready. All right, part of working with logarithms is taking kind of complex log equations or complex exponential equations and simplifying them so that we can solve them, or so that we can create a table of points so we can graph them. So we're going to go through some rules of logs, some math laws that apply always, that will allow us to take some kind of messy log equations and condense them into a single term that we can quickly solve. Okay, so these are kind of related to our exponential rules, and if we think about our exponent rules, if we have a multiplication problem with exponents, we add our exponents. If we have a division problem with exponents, we subtract our exponents. Logs work kind of the same. That'll help you remember how the log properties work. Our product property. So if, remember, product means multiplication. We can use multiplication in a log to be interchanged with addition of logs with a like base. And we can go back and forth between the two. So we can take a log and expand it into an addition problem, or we can take a log and we can condense it into a multiplication problem. Sure, yeah. Okay, so we're going to start with addition and we're going to move into multiplication, and then we're going to go backwards, okay? We have to make sure our bases are the same. If our bases are the same, we can write it as a single log, and we can multiply these two values. So looking at number 1, log base 2 of 7 plus log base 2 of 4 is going to be log base 2 of 7 times 4, which is 28. Looking at number 2, I have a common log, so log base 10, but it just says log, of 25 plus log of 4. This is going to give me log of 25 times 4 is 100. And here's a good picture of why we sometimes do this. Log of 25, I don't know. Log of 4, I don't know. Log of 100, 2. So this one is much easier to solve and work with than these two separate ones. And this last one, I have some variables in here. It's a log base 4 problem. I'm going to multiply my endings. I have 2x times 4x squared. 2 times 4 is 8. X times x squared is x cubed. Okay, now we're going to go backwards. I'm going to take a single log. I'm going to write it as an addition of 2 logs. And there's actually a whole bunch of different ways that I can write some of these because there are different factor pairs for whatever my terms are. So when I'm thinking of 6, 6 could be 1 times 6, it could be 2 times 3, and the bigger our numbers, the more varieties we have. So one thing to keep in mind, when you're picking your numbers to use, if you've got other numbers in your problem, try to match some numbers so that you can simplify terms. I usually try to avoid ones. So like here, I probably wouldn't do 1 and 6. I would pick my 2 and 3. So I'm going to break 6 down into 2 of its factors, and I'm going to write an addition statement. So log of 2 times log of 3. Oh, plus, sorry. Close one. Okay, 45, I have options. I could do 9 times 5. I could do 3 times 15. I'm going to avoid 1 times 45 because log of 1 is 0. So we don't usually write zeros, right? If I had other numbers, I'd try to match one of my other numbers, but I'm just going to pick one. I'm going to do 9 and 5. Log base 7 of 9 plus log base 7 of 5. I could have written log base 7 of 3 plus log base 7 of 15. And the last one, my term is 5x. That's really just 5 times x. Like there's not 2 good ways to do that. So we're going to write log base 2 of 5 plus log base 2 of x. Okay, so on Monday we're going to practice kind of, we're going to expand it and do math with it. We're going to condense it to solve it kind of thing. Okay, our next property is the quotient property. Quotient means division. And when we think of our exponent rules, division goes with subtraction. So when we think of our log rules, division goes with subtraction. So if I have a term here that can be broken into a division problem, I can write log base b of my numerator minus log base b of my denominator, and I can go in reverse. Okay, so we're going to start by condensing. Condensing means turn this into one term. So both of my terms here are log base 3. I'm going to divide my numerator divided by my denominator. 24 divided by 8 is 3. Log base 3 of 3. And it's not asking us to evaluate this, but what would that have to equal? 1. If these two numbers match, it's 1. So by doing that simple division piece, we're able to basically eliminate this term. Okay, looking at number 8, I have 2 log base 2's. They're being subtracted. Log base 2 of, I'm going to write it as 15 divided by 15. Log base 2 of 1, which would have to equal what?
0.
0. But also, what's something minus itself?
Nothing.
0. All right, last one. I've got exponents with variables here. Log base 4. I have x to the 9th on top. I have x squared on the bottom. I'm going to subtract my exponents to simplify. Log base 4 of x to the 7th. And here, obviously, I don't know what the value would be, but if this was a function, I could pick some inputs and I could calculate for some outputs and get it on a graph. Or if I knew what it equaled in the end, I could roll it to solve for x. Okay, now we're going to expand them. Expanding them, again, could have multiple possibilities. Okay, log base 8 of 4. That means two numbers that were divided ended up being 4. So I might use 8 over 2. I might use 16 over 4. I might use 64 over 16. I'm going to do log base 8. I'm going to use 8 over 2. Log base 8 of 8 minus log base 8, of 2. And this could be beneficial because log base 8 of 8 is 1. And I still have to solve my 8 of 2 there. Looking at number 11, my number is 1/3, so I could do log base 5 of 1 minus log base 5 of 3. I could also do 2 and 6. I could do 3 and 9. Whatever it is that I need, I could use 5 and 15. I'm just going to use 1 and 3. There would be a benefit of using 5 and 15 because we're in base 5. And last one, I have m over 7. I'm going to keep it as m over 7. Log. And this one doesn't show me a base, so it's an understood base 10. Minus log of 7.
Does it matter what order you're putting in?
Numerator first, denominator second. In addition, it doesn't matter the order. All right, last one, and then we'll let our brains rest. The power property. And when we think of the power property with exponents, it looks kind of like this. And we know that we would multiply those. And so we know this is going to be multiplication of some form. What this looks like is if we have m to the power of n, we can rewrite it as n times the log. Or we can go in reverse. If we have a multiplier out front, we can turn it into the exponent. When we have exponents in our work, if we're able to calculate them in our answer, we want to make sure we calculate them in our answer. So looking at 13, I have 5 times log base 4 of 2. So I'm going to turn this into log base 4 of 2 to the 5th. But I'm going to calculate 2 to the 5th, so this is going to be log base 4 of 32. I did 2 to the power of 5. Yeah. Looking at number 14, my multiplier is 7. I'm going to move that to my exponent. Log base 2 of x to the 7th. And number 15, this is another one I'm going to be able to calculate. Log of 8, base 10, to the 1/3. But I can do 8 to the 1/3 because that means cube root. And the cube root of 8 is 2. So this is log of 2. And this is another one I could check because I could type this whole common log in my calculator. I could type this whole common log in my calculator. I could type this common log in my calculator. Okay, now we're going to go backwards. So we're going to take our exponent. We're going to move it to our multiplier position. So log base 2 of 8 to the 7th. Don't calculate this. Okay, don't turn this into like a gajillion whatever. Move that 7 out front. log base 2 of 8. Just like that. Here I have a multiplier. I'm about to give it another multiplier when I move this exponent. So I move my exponent out front. And to simplify this, I'm going to distribute these. So this is going to be 3x minus 1 times log of 4. And if that equaled something, like if I had to equal something on the other side of the equation, I would start solving for x, right? All right.
Negative, you just move it down.
For this x minus 1?
Yeah, you just move it.
Yeah, you just put it out in front as a multiplier.
Or would it be 3x minus 3?
Yes. Thank you. And last one, log base 7 of the square root of w. Notice this doesn't have an exponent. In order to do my rule, I need an exponent. So I'm going to rewrite this as w to the 1/2. Remember, that's a square root. And now I'm going to move that 1/2 out in front. Log base 7 of w.